So in this video we're going to use a vector-based approach to finding a force. So in this problem what we have is a 500-pound crate sitting on a ramp, and the ramp is inclined at a 30-degree angle. And we want to know what the force is that's needed to keep this crate from sliding down ramp. And the idea is if we have a 500-pound crate, there's going to be a force vector due to the acceleration of gravity pointing down towards the center of the earth. And that force vector is going to be 500 pounds in size. The force vector is going to be the weight, the size of it is going to be given by the weight of the crate. And what we want to do is think about or visualize establishing an XY coordinate system right here. And if we do that, then this vector G, the force due to gravity pointing down towards the center of the earth, is really easy to represent. So the force acting on the crate is going to be 500, because that's the size of the force, 500 times a unit vector, a vector of length 1 that's in the right direction. So what we want to do is find a unit vector pointing down towards the center of the earth. And because I've imposed an XY coordinate system right here, the unit vector pointing down is going to be the vector 0, -1. No x component, and -1 points me downwards. So this vector is the force vector acting on the crate. And then the idea is that the force vector acting on the crate can be decomposed into two forces. There's a force component of the force that's acting parallel to the ramp, and there's a component of the force that's acting perpendicular to the ramp. And only the component of the force that's parallel to the ramp helps or tries to get the block to move down the ramp. The component of the force that's perpendicular to the ramp maybe serves to increase the coefficient of friction, but it isn't going to make, if it's perpendicular to the ramp, it's not going to make it move down the ramp. So what we want to recognize is that this force component here, the component of G that's parallel to the ramp, is actually the projection of G onto the ramp. So we were just working with projections in the previous video. So what we need to find is to find the projection of G onto the ramp. I'm going to represent the ramp with an R, and this will be a vector, and what we're going to need to know is the size of that vector in order to know the size of the force that we need to push up ramp to keep the force component that's down ramp from moving the block down ramp. So what we need to do is think about how can we calculate the projection of G onto the ramp, and it's actually going to turn out to be pretty simple, because if we know the angle the ramp makes with the horizontal, and the x-axis is horizontal, then we know the angle that we make with respect to the positive x-axis. This angle right here is a 30-degree angle. And from trigonometry, then, we can easily make a unit vector parallel to the ramp. So remember, from trigonometry, we can, if we know an angle, then we can make a unit vector based on the unit circle given by the cosine of the angle and the sine of the angle. And because cosine theta, sine theta is a unit vector that lives on the unit circle, the circle of radius 1, this is actually going to be a unit vector, a unit vector. So if we plug in 30 degrees, so we plug in 30 degrees here, cosine of 30 degrees comma sine of 30 degrees, we actually have a unit vector parallel to the ramp. So all we need to do is project the force vector G onto that unit vector that's parallel to the ramp, and we'll have the component of G parallel to the ramp. And then this is a special angle, so the cosine of 30 degrees is the square root of 3/2, and the sine of 30 degrees is going to be positive 1/2. So this is a unit vector that is parallel to the ramp, and we just need to project G onto it. So this projection is going to be given by, we're projecting g onto r hat, so it's g dot r hat divided by the size of r hat squared, and the vector would be times r hat to make it a vector, because this piece is a scalar. But what we want to recognize is, because this guy's on the unit circle, he has length 1, the size of r hat is 1, so this denominator is actually just 1 squared. So this simplifies to g dot r times r. So g is the vector 500 times the unit vector 0, -1, dotted with r hat, but r hat is the vector √3 over 2, 1/2. And then when we take, and then we're times the vector r, so we're times the vector √3 over 2, 1/2. And then we take this dot product, we get 500. So this is where dot product properties are nice. We saw that if we had a scalar times a dot product, we can do the dot product first and then multiply by the scalar. From, I think that was property 3, if I remember correctly. So it's going to be 0 times √3 over 2 plus -1 times 1/2 is just -1/2. And then it's times the vector to get the projection vector. So √3 over 2, 1/2. And when we do this, we get -250 times √3 over 2, 1/2. And so this is the vector pointing down the ramp, but here's what's nice, because this is a unit vector. We created it from cosine of 30 degrees, sine of 30 degrees, and we know that cosine squared plus sine squared equals 1. This vector has length 1. That means that this scalar -250 is the size of the force that we need to apply to the block to keep it from moving down ramp. So we need to push up ramp. We need a force to push up ramp with 250 pounds of force. If we wanted to know the vector component that was perpendicular to the ramp, we would take advantage of the fact that this guy right here, this perpendicular component, would just be g minus the component of g parallel to the ramp. So we could get, and in the previous video we called this guy w sub 2. That's kind of a lame name, so maybe call him ramp perpendicular vector. So if you want the component of the force vector that's perpendicular to the ramp, we would take the our gravity force vector here, 500 times 0, -1, and then we would subtract the projection from it. So we would subtract the -250, √3 over 2, 1/2. We have a double negation, so that's going to be a plus. Don't erase your 2. And then we would just work this out. 500 times 0 is 0. 500 times -1 is the -500. And then plus, distribute the 250 in. We're going to get 125 times the square root of 3, 250 times 1/2 is 125. And then to find the vector, we just add corresponding vector components. So 0 plus 125 square root of 3, -500 plus 125 is going to be what? -375. So that would be the orthogonal component of g, the component of g orthogonal to the ramp. And if we needed to know the size of the force, that was perpendicular to the ramp, we would just calculate the size of this vector right here. And we know how to calculate the size of a vector. We would take the square root of the sum of the squares of the vector components. And what you'd want to notice here is some stuff could factor out, and you'd probably want to factor as much out as you could before you did that calculation. So for example, 25 would go in there, what, 5 times? Oops. Pull a 25 out, and we would get 5 √3, and 25 is going to go in there 12, 15 times, I think. Is that right? So it looks like we could have factored out the 5 as well. So factor out the full 125. And if we factored out another 5, that would make this -3. We would want to check the work here. 125 times -3, -375. So that looks good. And so what we wanted to do, if we wanted to know the size of the perpendicular force, we would just say it's going to be 125, the scalar, times the size of the vector it's being multiplied by. So it'd be times the sum of the squares of the vector components. And we could do that calculation pretty easily. So the size of the force perpendicular to the ramp would be 125 times the square root of 3 squared is just 3. And -3 squared is 9, so we'd get a 12, which is the same as 4 times 3. So we would wind up with 100, square root of 4 is 2, 125 twice is 250, so we get 250 square root of 3 as the size of the force perpendicular to the ramp. So again, this is just a vector-based approach. You don't have to use a vector-based approach to do these, but for the purposes of our current homework assignment, a vector-based approach would be expected because that's what we are working on right now. That's what the course objectives are. Vectors and working in three-dimensional coordinate systems, dot products. So use the tools that we've been using when you do the homework assignment.